Hello students, this is another short video on some nomenclature. So this file has been uploaded to Canvas, and let's look at, let's go through a few of them, let's look at some techniques. So I would say the most important technique for nomenclature is to identify what type of chemical you have. Do you have an ionic compound? Do you have a covalent compound? Do you have an S-block metal ionic compound? Do you have a P-block metal ionic compound? Do you have an acid or a base? So that's my recommendation for you. Okay, so for example, let's see number one. We identify number one as a covalent compound, so we know we have nonmetals only. So sulfur and oxygen are both nonmetals. And so we use our covalent compound rules. We know that we use prefixes. So for example, 1 is mono, 2 is di, 3 is tri, 4 is tetra, 5 is penta, 6 is hexa, 7 is hepta, 8 is octa, and 9 is nonna, which randomly is also grandmother in Italian, and 10 is deca. Okay, there's a generic rule that says you don't begin a word with mono. So this 1 to 2 definite proportion for SO2 that we have here, rather than monosulfur dioxide, it's just sulfur dioxide. The prefix di represents the fact that we have 2 oxygens. Let's go down over here, actually, number 33. So carbon disulphide similarly is the same naming family as sulfur dioxide. And again, we don't preface the word with mono. That's a generic rule. So you'll never begin a name with mono. But we do have other prefixes. So the disulphide, we have 2 sulfurs. Notice that the first element is the regular elemental name, so carbon for number 33 and sulfur for number 1. But the second element in a covalent compound takes the suffix IDE, so rather than disulfur, it becomes disulfide, and rather than dioxygen, it becomes dioxide. Okay, let's see if we can find any more for that family. Yeah. So number 12 is same naming family. We have carbon monoxide. It's not monocarbon monoxide because we don't begin a name with mono, but it's just carbon monoxide. We can begin, if we look at number 37, we can begin a name with a prefix. That's okay, so long as the prefix is not mono. So in 37, we have dinitrogen oxide, because we have a 2-to-1 ratio of nitrogen to oxygen. Another way you could say this is dinitrogen monoxide. There's nothing wrong with having the monoxide here. So that would be fine too. Looking at number 18, we have carbon dioxide. Number 21 is a good example of the same family. We have diphosphorus pentoxide. Most people would drop the A, so you just have pentoxide. But just as a learning tool, this shows you that you have a prefix number of oxygens. Okay, so these few examples have all been the same family, and so they follow a general naming rule, and that naming rule is prefixes. Okay, let's now look for examples of S-block metal ionic compounds. So we see, and I'll try and find a simple example first. Let's see if we can find one. Nice simple example. Simple meaning I don't ideally want any polyatomics. Okay, so if we go all the way to this page here, this sheet which has number 1 here, we can see NaCl, sodium chloride. So this will follow a different naming convention. We know it's an S-block metal ionic compound because sodium is in the S block and it's a metal. And we know it's an ionic compound because sodium is a metal and Cl is a nonmetal, and ionic compounds typically have a metal and a nonmetal. Notice there are no prefixes. So S-block metal ionic compounds differ from covalent compound nomenclature in that we have no prefixes. So just sodium chloride. Again, the first element takes the regular elemental name, but the second element, rather than chlorine, we have the suffix IDE, and this reminds us that it's not the same as chlorine. Remember, chlorine has 7 valence electrons, but chloride has 8, well, has technically no valence electrons because it's gained an electron and its valence shell has become core. But to remind us that the Cl next to Na is not the same as the Cl element. So this is an ion and not an element. Another example here is number 25. We have potassium bromide. Again, it's an S-block metal ionic compound. It's a 1-to-1 ratio. And there are no prefixes. We can tell there are no prefixes when we look, for example, at number 6. We can see magnesium bromide. Here it's a 1-to-2 Joseph-Proust definite proportion. But we don't put dibromide. Why do we not put dibromide in the nomenclature? Because there's no need. I know magnesium is in group 2, and I know any metal in group 2 when it forms an ion has a +2 charge. I know bromine is a halogen, and I know halogens, when they become halides, so the ionic form of the halogen, has a -1 charge. I'm quite capable of adding 2 -1s and realizing that I do need 2 -1s to match a +2 magnesium charge. So the definite proportion 1-to-2 is inherent in my knowledge of the groups in the periodic table. So there's no need. It would be additional, adventitious, unnecessary information to add any prefixes here. Let's look at aluminum oxide here. Again, I've got 2 aluminum and 3 oxygen. There's no need for prefixes. Now, aluminum is not an S-block metal, but it kind of behaves like an S-block metal in that it only has 1 charge. And that 1 charge is 3+. So if I've got something aluminum with a 3+ charge, and I've got something else, oxide, with a -2 charge, what possible ratio could I combine them in to have an ionic compound which has a net 0 charge? So remember, ionic compounds have net 0 charge. Well, +3 and -2 both factor into 6. What do I do to +3 to make +6? I scale it by a 2. So that's where the 2 from aluminum comes from. What do I do to the -2 charge of oxygen to make -6? I scale it by 3. So that's where the 3 for oxygen comes from. And so I get my Joseph-Proust definite proportion, and there's absolutely no need for prefixes. Okay, let's go back and look at some S-block metal ionic compounds with polyatomic ions. So remember, polyatomic means more than 1 atom with the charge distributed. Let's look at number 5 and number 7. So lithium hydroxide, we know hydroxide is OH-, and we know that it has a negative charge. We know lithium, because it's a group 1 metal, has a +1 charge. So we have a 1-to-1 Joseph-Proust definite proportion between lithium and hydroxide in number 5. If we then move to number 7, we have sodium sulfate. Notice no prefixes, no need. But we have a 2-to-1 Joseph-Proust definite proportion between sodium and sulfate. Sulfate comes as a package, SO4 2-. We need 2 single positive sodiums to cancel the 2- charges of sulfate. There's no need to use parentheses with a monatomic ion. So sodium is not in parentheses, it would be incorrect to do so. We just scale it by a number 2, and there's no need to represent that in the nomenclature because, again, it's S-block metal ionic compound. So we don't put parentheses around monatomic ions, but we would put parentheses around polyatomic ions. So for example, and this will be the last example in this video, let's look at magnesium bisulfate. Another name for bisulfate would be magnesium bisulfite. Another name would be hydrogen sulfite. So that's another way you could write by here. You could call it hydrogen. We know that magnesium is in group 2. It's got a +2 charge. And we know that sulfite, SO3 2-, has a 2- charge. So hydrogen sulfite or bisulfite has an H+ added to SO3 2-, which gives it a single negative charge. So that's why I need 2 of them. I need 2 single negative charges to cancel the +2 charge of magnesium. Now bisulfite is a polyatomic ion. It's more than one atom with the charge distributed around it. So in order to duplicate it, I need to put it in parentheses and then apply my duplication, which in this case is 2. So again, put polyatomic ions of which there's more than one copy in parentheses before you apply the duplication. No need to do so for single copies of polyatomic ions. And whenever you have monatomic ions that are scaled, there's no need to use parentheses. So these are the general rules for S-block metal ionic compounds and any other ionic compounds that behave like S-block ionic compounds insofar as they only have one type of charge that the metal can adopt. So this concludes this short video.